Welcome to this third module of our course on open channel hydraulics. Here we will be discussing in this module that how the concept of energy and how this momentum principle, that is energy principle and momentum principle, that we use for computing various works of hydraulic engineering, how these are applied to understand some of the problems of hydraulic engineering, to solve those problems. Well, to start this module, let us start with the topic, that concept of specific energy. Well, of course, we have already discussed some of the issues related to specific energy, but still we will start with the start from that particular point where we left earlier. That is, what we did earlier, that we could see what we mean by energy, that we have already understood well. Then we could see that energy of flowing fluid, that we can divide into three components, like that potential energy, that the energy derived due to its position. Then we talk about pressure energy, means the energy due to pressure, and then we talk about kinetic energy, that is that energy derived by the fluid due to its motion. So, these three components of energy are there. I mean, just when we talk about total energy, then we say that summation of all these energy is the total energy of the flowing fluid, right. And then there is another term that we call as energy head. Now, what is the difference between energy and energy head? That part also we have discussed. Basically, by energy head we mean that energy per unit weight of fluid. Of course, flowing fluid we are talking about. So, energy per unit weight of fluid is called as head, energy head. Now, when we write the expression for this energy head, now you can concentrate on the slide, that is, say we can call that energy head total energy per unit weight of water, and of course, fluid means in hydraulic engineering we talk about water at a channel section. And say when we say energy, then we always talk about that energy at a particular section. And then potential energy, as we could see, it is due to the position. And when we say that in a channel, when we say in a channel, say this is the channel, then by potential energy always we talk it up to the channel bed. Say at a section, when we talk about potential energy, then it is up to the channel bed. So, it is coming as jet. And say water is flowing up to this much level, and then as we know that point was also discussed earlier, that is depth, that when we say the depth of flow in a vertical direction, this is different, and when we say the depth of a flow section, then it is the flow section, means it is a section normal to the flow direction. So, that will be different. So, from that point of view, this pressure energy is basically in open channel flow, it is coming as the y, but of course, when there is a slope theta, then we can write it as y cos theta, that was discussed, and this theta is basically nothing but the slope of the bed, that is SB, bed slope. Well, then kinetic energy. Well, that kinetic energy is again half mv square, and then when we just derive that expression for unit weight of fluid, then we get that as v square by twice g. And now, if we recall our discussion that we carried out earlier regarding that energy coefficient alpha, then we know that when we talk about energy, then we know that energy is in fact is different. When we talk about energy at a particular flow section, at different point it will be different, because the flow velocity is in reality it is not equal. So, a coefficient comes. So, actual kinetic energy will be written as this kinetic head multiplied by that alpha, energy coefficient alpha, or we called it as that as a Coriolis coefficient. So, these total energy, if we sum up, then we say that energy is equal to energy, and that is normally written as H, indicating head, energy H sometimes we write as E also, but in open channel flow we generally use this symbol H to write this total energy, that is Z plus Y cos theta plus alpha V square by twice G. Well, with after recalling these things what we did discuss earlier also, then we can now try to see what we mean by specific energy of open channel flow. Well, specific energy of open channel flow. Again, from this particular line, that is H is equal to Z plus Y cos theta plus alpha V square, for say theta is very small, suppose for theta is approximately equal to 0 and for alpha is equal to 1. That means, by alpha is equal to 1, what we mean that the velocity that is velocity variation within the cross section is say very minimal, very small, and as such we can consider that alpha to be equal to 1, that is say velocity coefficient is not that much significant. In that case we can write this is equal to Z plus Y plus V square by twice G. Okay. Well, then when we say about specific energy of open channel flow, then we talk about the energy with respect to the channel bottom, with respect to the bed of the channel. That means, in this case we are here, say earlier when we were doing, then this Z is from the datum. Say this is our datum, from that datum we got the Z. Now, our datum itself is, we are measuring the energy with respect to the channel bottom. So, this is our datum. So, this Z term is not coming at all here. And so, our specific energy we can write that E is equal to Y plus V square by twice G, Y plus V square by twice G. That means, by definition what we can write, before going to the specific energy diagram, let me write the definition here, that is energy per unit weight of fluid with respect to channel bottom, So, that way we can write what we mean by specific energy. Well, now with specific energy, this equation E is equal to, again let me keep the equation here, E is equal to Y plus V square by twice C. Now, we can draw a graph, relating these term, relating this E and the Y. Why? Because here this V square by twice Z, V square is nothing but we can write that is Y plus it is Q square by say A square by twice G, Q square by A square into twice Z, Q by A is equal to velocity. Well, now when we write this as Q square by A square, that means again A is a function of Y. Now, whatever may be the section, this area is always a function of Y. With the increase of depth, our area increases, with the decrease of depth, area decreases. So, it is in some form it is also always a function of Y. So, as such, that means what we can say that E itself is a function of Y. Specific energy can be considered as a function of Y, it is a function of Y rather. And then, so when we plot this value, when we plot E versus Y, that is change the Y and calculate what E is, and if we plot these things, then we get a graphical plot of E versus Y, and that particular plot is referred as specific energy diagram, Well, now, without going to any definite value, let us take say in this direction we are plotting Y, and in this direction we are plotting E, and let me draw the channel on this side. This will indicate the different depth we are here. Now, from this expression that E is equal to y plus v square by twice z, from this expression we can see that what will be the line for E is equal to y. E is equal to y, this line will be definitely a line drawn at 45 degree to this axis. So, if I draw a line 45 degree, this line is nothing but E is equal to y. Okay. Well, then let us see what else is there. The second term is v square by twice z. Well, so this v square by twice z, v, even v is negative, but it is v square, then it will always be positive. So, v square by twice z is always a positive term, it is always a positive term. So, our specific energy diagram, that is the curve of energy versus E, energy E versus depth y, will be, because when E is equal to y, then we are getting this line, but E is actually something more than y, E is something more than y. So, that way it will be always on the right side of this line, always on the right side of this line. Okay, because E is, suppose E is y is this much plus something. So, it is always coming to the right hand side, and then if we plot this curve, then we will see that we will be getting a line like this. We will be getting a line like this. Well, so this line, we are getting a single line. This line is for a given discharge. If we just see this equation, E is equal to y plus q square by a square by twice z, then we understand that if we change the q, then entire things are changing. So, here we are talking E as a function of y, we are writing E as a function of y, when, because y and a are function of y, y is obviously y and a is a function of y, but q we are considering as constant, and that is why we are writing that E is a function of y. So, this is for a given q, this is for a given q, this line is for a given q. Well, now you can just see peculiarity of this particular curve, that say if our discharge is fixed, say discharge is fixed, q is like that, and it is having this much of depth of flow. Now, when our depth, if we suppose by any means, suppose let me change the slope, if we are changing the slope, then our depth will come down, it will reduce, and when depth come down, your E from this part it will be less, but when depth come down, when q remains same, our velocity increases. So, this component will increase. So, that way with the change of depth, E is coming down sometimes and then it is again increasing, and then we get a minimum value, For this q, we have specific energy minimum, we have E minimum, and for that E minimum we are getting a corresponding depth. For this depth we are getting minimum specific energy for a given discharge. Well, now if I take another discharge, that is if I increase the discharge, then I will be getting another curve, this curve will be coming like this. This is going like this, and this q1 if I write, this is greater than q. Then if I draw another, if I increase the discharge further, then I will be getting another q, I will be getting another curve, and this curve will be like this, Okay. And suppose it is q 2, then this is greater than Q1, it is greater than Q. Well, so that way with the increase of discharge, we are getting our lines get shifted to little higher side, and then we are getting some point joining that all here, all in this point we have our minimum specific energy, we have minimum energy. Okay. But this minimum energy correspond to the discharge Q2, and this minimum energy correspond to the discharge Q1, and this minimum energy correspond to the discharge Q. Well, and this set of curve, that is the specific energy diagram, has the peculiarity that this line is asymptotic to the line drawn at 45 degree. This line you can refer, this line is drawn at 45 degree to the E axis, and these lines, if you just increase the Q, this will keep on going. If you just increase the depth, it will be just about to touch this line, but it will never touch, it will be asymptotic to this line. And similarly, it will be asymptotic in this direction, it will be asymptotic to this line. So, it will be going like that. Well, and as we were explaining that when we talk about minimum specific energy, then the depth corresponding to minimum specific energy, this we call as critical depth. This is called critical depth. So, critical depth we call as critical depth, depth corresponding to minimum specific energy, minimum specific energy. Okay. Well, that means all these things we are talking about again a particular channel section, because say when we are saying area is a function of y, definitely if our channel section changes, that function will also change. So, our same equation will not hold good. So, equation means same shape will not be getting. So, that way for a given section, for a given discharge, we get a relation that which says that it will give us a minimum specific energy, and that minimum specific energy correspond to a depth, particular depth, and that depth we call as a critical depth. And then there are another important point that we should know is called alternate depth, and for that let me draw this diagram again here. Let me draw like that, and then we got that for the minimum specific energy E minimum, we are getting a depth, and that is giving us critical depth. That depth is called critical depth YC. Now, for a different other than this E minimum, that is if it is something higher than E minimum, for any specific energy E, we are getting a depth, this one, that means say this depth and this depth. If I draw a line, if I draw a vertical line through this point, then it represents that for this energy we can get corresponding to a depth, this one, and the same energy we can get corresponding to a depth, this one. Okay. So, now this is say y1 and this is y2, this is y2. Well, so this y1 and y2 we are getting two depth, this y1 and y2 we are getting two depth, and both the depth, for both the depth we are getting the same specific energy, for both the depth we are getting same specific energy, and that is why this depth has a special relationship and this depth has a special name. These depths are called alternate depth, these depths are called alternate depth, alternate depth. So, this y1 and y2 are called alternate depth. These are corresponding to a specific energy E. Now, then what are the speciality in these? Let me just draw this diagram again, and then let me explain another point here. Let us discuss. Say this is the specific energy diagram, and then we are having this point again. With the increase of discharge, this can be line can go up, and then these are suppose critical depth point, and then what we can have that, well, this is one critical depth y c, and this is y 1, sorry, and this is y 2. Okay. y 1 and y 2. Well, now when say we are having this minimum depth, minimum specific energy for this depth. Now, for any other energy we have a depth here and another depth here, and when this depth is less than the critical depth, when this depth is less than the critical depth, this zone and where we are getting the depth is called actually supercritical. This is called supercritical, and then on the top it is called subcritical. Of course, that we discussed when we were discussing the classification of flow itself, what is subcritical flow and supercritical flow. And here also the same thing, just we are recalling that this is a depth, I mean depth y 1 is a depth in the supercritical region, and then this y 2 is a depth in the subcritical region. Well, now these are some of the point that we have discussed, that is the critical depth and alternate depth. Now, there are some relationship between this critical depth and the alternate depth. That means, if we know suppose if we know a alternate depth, if we know suppose y 1 and if we know the critical depth y c, then we are in a position to find out what will be our y 2 using that relationship, or if we know both y 1 and y 2, we know that for that particular flow what is our critical depth. So, these are all possible. Well, now let us see that we are talking about this minimum specific energy E minimum. Now, mathematically from that condition, can we have some expression? Well, that say we are always writing E is equal to y plus v square by twice g. Well, and then from here we can definitely write that E is equal to y plus q square by b square, or say q square by a square, that area, let us make it general, q square by a square into twice g. Well, now, at the point where specific energy is minimum, we are talking about change of specific energy with respect to y. So, at the point where specific energy is minimum, at that point we get that dE dy that must be equal to 0 for critical condition. That means, for critical condition, what we can write for critical condition, that is for minimum specific energy, what we are getting, that dE dy is equal to 0. That means, at this point our slope, this slope is 0. So, that way we are coming to that point, that dE dy is equal to 0. And so, what is dE dy? This implies that if we do it, then it is 1. Then area is actually a function of y. So, we can just differentiate it. If we just differentiate it, then we can have say q square by twice g, let it be, then a to the power, basically it is a to the power minus 2. So, what we will be getting, say minus 2 into a to the power minus 3, that is what the differentiation of 1 by a square, and in place of y, as we have used this a as the variable. So, we will have to write here dA dy. Well, now in a channel, when we talk about this area A and say depth y, then by dA dy means if the y changes by a small amount dy, if the y changes by a small amount dy, then how much is the change in this small area dA, how much is the change in small area. Basically that is what dA and dy. Then if I write this as the top width T, that from here to here, then in fact what is this dA, this is nothing but this top width into dy. Rather than going for differentiation on all these things directly, we are writing in a very straightforward way from the actual figure. So, dA is equal to T into dy, or we can write that dA dy is equal to the top width. Well, so by replacing this term, what we can have? Well, now we were writing dE dy is equal to 0. That means 1 plus q square twice z, then this part, this is equal to 0. Well, this implies that 1, and this minus sign is there, so it is coming 2 and 2 is getting cancelled. So, we can write q square by 2 is already getting cancelled, q square by z, then this a to the power minus 3 means a cube I can write in the denominator, and this dA by dy, that is from here we can write it is equal to T. So, this is equal to 0. So, this leads us to one expression that q square T by GA cube is equal to 1, q square T by GA cube is equal to 1. Well, so this is a very important equation or important relation so far a specific energy is concerned, and this equation we will be using for say computing our various relation for say for computing critical depth we will be using this equation, and then for when we will be computing say other, when we go a step ahead, suppose we will be doing gradually varied flow, there also we will be requiring this particular relation for computing critical depth, and to know whether there will be gradually varied flow or not. So, for different aspect we will be requiring different purpose, we will be requiring this relation, and so we should always try to remember this relation. And why I am emphasizing this point? Because when we just simplify this equation, that means if we write this expression, this is a general form. Now, if we write this expression for a rectangular channel, then this equation will take a more simpler form, and generally we use those expression and we remember those expression, but in reality we should remember this original relation which from where we will be deriving the other steps. Well, now again as we are finding that this specific energy is, again going back to this line, this specific energy E versus y relationship, and this curve is for a particular discharge, Okay. Now, can we have some relation, because as we see that discharge is also say increasing, if we increase the discharge our line changes, Now, there can be another relation that we can derive, this is called depth discharge diagram. Like specific energy diagram, we can have another diagram that we call as a depth discharge diagram. Again starting from the same relation, that is say E is equal to y plus v square by twice z, and from there we can write E is equal to y plus say q square by twice z by a square, this part, and then from here let us just see how q will vary if we change the depth and keeping the E constant. Let us, our target is that, I mean this diagram, that is depth discharge diagram, will show us that if we keep on changing the y, keeping the E constant, then how our discharge will vary. Well, so let me write this implies that E minus y is equal to q square by twice g into a square, and then our target is to know q square. So, q square is equal to twice g a square into E minus y. This will give us q is equal to root over twice g a, then root over E minus y, root over E minus y. So, this is what the relation we are getting, q versus y, and then from here also it is clear that energy is a function of y, already we know. So, y is there. So, this area is a function of y. So, rather energy although a function of y, we are now talking about a constant energy. Suppose energy is constant, then what are the other values, say area and y. What are the other variable? These are area and y, and these are all function of y. So, keeping energy constant, we can have a relationship that if y changes, how this q changes, because this implies that q is also a function of y, q is a function of y for constant E, for constant E. Well, now let us see that how we can derive this relation. This curve will be taking a shape, this curve will be taking a shape of this one. It will be coming like this, it will be coming like this. That means, in this direction we are writing q, and in this direction we are plotting y, and there we are getting a q max at this point, maximum q, and then this is for a particular energy E. This is for a particular energy E. If our energy level increases, this level will rise, and that way we will be getting another curve like this. If our energy level increases, we will be getting another curve like this. So, this is similar to the diagram of specific energy diagram, we can have a depth discharge diagram. Well, now in this depth discharge diagram, here also we can see mathematically how this expression for q max we can give, or that what can be the condition for this maximum q max. Well, we know till now that for minimum energy, the depth, corresponding depth is called critical depth. Now, if I draw the channel here, then for this maximum discharge for a given energy, what depth we will call this one? What will be the relation and what this depth will be? Will this be critical depth or this will be something else? So, let us just see that particular aspect. Let us see here itself, let me write, that is we have already got one expression, that is say q is equal to root over twice g a E minus y. Okay. Now, what will be for maximum discharge, for say maximum discharge, what we will get for maximum discharge? dq dy should be equal to 0, dq dy should be equal to 0. Okay. Now, here these two a and these two are function of y. So, it is basically a this function we can say call as a or refer as a product of two variables. So, we can write that expression dq dy. Well, so let me write here say q is equal to root over twice g into a root over twice g into a into root over e minus y, and then what will be our dq dy. So, dq dy we can write this is equal to root over twice g will remain as it is, then we can write that this first term into the differentiation of the second term, and let us write this as say e minus y itself and differentiate it. So, e minus y to the power half. So, that will be coming half will be coming. So, we can write half into root over so e minus y to the power minus half, 1 minus half. So, this is minus half coming, and then let me put a bracket here. Then again differentiation of this term. So, this will be coming minus 1, because we have differentiated root over e minus 1 with respect to e minus 1. That is why we are getting this relation, and then we are just differentiating this again with respect to y, we are getting minus 1. Then plus, say we have already done first into differentiation of the second. So, let me do second e minus y into differentiation of the first, that is dA dy. Well, now this relation we can write as dq dy is equal to 0. So, I am writing this is equal to 0. Well, so twice g already we can cancel, then this will become, we can write, this implies say 1 by root over e minus y, 1 by root over e minus 1, that part, and a negative sign is there, this is coming negative sign, and then this 2 is there, half is there. So, 2 is coming, area is there. So, area is there, then plus this term will be there, root over e minus y into, and dA dy we can write, because dA dy we know that it is nothing but equal to t. So, we can write this as t. Well, and then this is equal to 0. So, multiplying this by root over e minus 1, what we will be getting, minus a by 2 plus e minus y into t is equal to 0. Now, what is e minus y? What is e minus y? Say we have already from our earlier expression, we got that e minus y is equal to, we have e minus y is nothing but, from this you can see e minus y, if I just square this part, then it will be q square by twice g a square, q square by twice g a square is equal to e minus 1. From this relation itself we will be getting that one. So, in place of e minus y we can write this expression. Well, so this implies say minus a by 2 plus, then e minus y is equal to q square by twice g a square into t, q square by g y s, and this is equal to 0. Or now we can write it in the form that this implies, taking that to other side, q square t by this 2 and 2 we can just, okay, let me write here 2 g a square is equal to a by 2, and this will lead to ultimately, say 2 cancel, a is coming this way. So, it is q square t by g a cube is equal to 1. Well, so the relation what I am getting, let me write it here, that is q square t by g a cube is equal to 1. Now, what this implies? What this implies? If we recall, the relation that we got earlier for specific energy is q square t by g a cube is equal to 1, and then for this discharge also what we are getting is again q square t by g a cube is equal to 1. That means, we are getting the same condition, and same condition means this condition is nothing but the condition of critical flow. So, to get the maximum discharge, what depth we are getting, this is nothing but the critical depth. Again, this is nothing but the critical depth, and if depth is more, then we can get for any other discharge q here, suppose depth we are getting this one, and that is also alternate depth that we were discussing earlier, and that way we can say that here this will be subcritical flow, here this will be supercritical flow. Now, these relations, that is the depth discharge diagram and the specific energy diagram what we are getting, all this relation we can use for analyzing many problems that we frequently encounter in the hydraulic engineering. Say when a flow is moving, let me just give you some practical example. Say flow is moving in a channel and then there is a hump in the channel, means there is some rise in the bed in the channel. And because of the rise in the bed, when we talk about say specific energy, that is with respect to channel bed. So, as there is a rise in the channel bed, there will be change in the energy. Now, because of those changes, how the flow depth will change, that we will be knowing from this sort of relationship. And similarly, when suppose a channel is carrying water and it is suppose somewhere the channel is narrowed down, somehow the channel is narrowed down. Then of course, from this diagram, depth discharge diagram, we can derive another diagram, that is depth versus unit discharge. Unit discharge means discharge per unit width of the channel, what it is. Well, so that will be coming later, and using that relationship we can find out, say when a channel is carrying some discharge and then when it is narrowed down to a particular level, then definitely the depth, suppose it was here bigger, then it is coming down and it is becoming narrow, then depth here and depth in the upstream side will be different. Now, how this depth changes and how we will compute this depth. So, those part we will be doing by studying this sort of graph, and of course, we will be deriving some mathematical relation for those things. Well, then we need to discuss another topic, that is what we call as critical slope, steep slope and mild slope. Well, let me just explain what we mean by critical slope, then these things are automatically coming up. Well, now in a channel, let us consider a channel, then we are getting a for a particular discharge, we are getting a depth this much, and that is say uniform flow, we are getting a uniform flow depth, this was normal depth y n. Again we are going back to our study of uniform flow. So, we are getting a normal depth y n. Now, having the same discharge, if we change our slope, then we are getting our normal depth will be different. If I write this as y n 1, that means first normal depth for this slope, this is S b, this is S b, for this slope my normal depth is changing, this is y n 2. Now, we know that means for different slope we can get different depth of flow as normal depth, given the other section and discharge are same. Now, suppose for a particular slope we are in a we have got such a slope that for this slope we are getting a normal depth y n, and this particular depth itself is nothing but critical depth, because already we know that for a particular discharge we can have a critical depth y c. Now, if we get a slope such that for that particular discharge q we are having uniform flow depth such that this uniform flow depth y n is nothing but equal to y c, that is this depth is critical depth, and this particular line of course we call as critical depth line CDL, and that part we will be discussing in detail when we will be going to our next topic, that is gradually varied flow. But here just you know that we can have a slope where we can have uniform flow at a depth of critical depth. That means, with minimum energy, for this discharge the water is flowing with minimum energy, and that particular slope is called critical slope. If this slope we will write as critical slope as C. So, that is what the concept of critical slope, and then to find it mathematically or from our other relation, if we use Manning's equation, then we can write say q is equal to 1 by n, then we can write r to the power 2 by 3, then s to the power half. Now, when we say that this equation, suppose we are writing from this condition, that is when it is in critical condition, flow is critical, then our hydraulic radius we can write as RC, that is hydraulic radius corresponding to critical depth, because it is in critical condition, and then this slope we will write as SC. So, if we write it, this is, of course, we have written this velocity expression, and it must be multiplied by area, this must be multiplied by area to get the Q. So, it is also AC. Area means this is also a function of y. So, this AC means the depth at critical condition. So, with this expression we can find out what is our SC. So, SC is nothing but, we can write SC to the power half is nothing but this will be Q into N divided by RC to the power 2 by 3 and then AC. So, that way you can write, or SC we can write that this is to the power 1 by this is square. If I square it, then this will be square. So, this way we can write one expression for SC, and here our this R is critical and this is critical. So, using this critical term we can find out, using this critical term we can find out what is our critical slope. Okay. Now, to talk about this steep slope and the mild slope, that is if, well, let me rub this part. Now, what we have got that if y is, if SC concept we have got. Now, if the bed slope is greater than critical slope, then it is called steep slope. This is called steep slope. And then if bed slope is less than critical slope, then it is called mild slope. It is called mild slope. Now, coming to this condition, if we talk about say you refer to this diagram, say we are talking about critical slope here SC, and for that we are getting this much of depth yn, which is nothing but equal to the critical depth. Now, if our slope exceed this value, then it is steep slope, and when slope is more than that, depth will definitely come down, like this. And then if we reduce the slope, then depth will go high. For steep slope we are getting lesser depth than the critical depth, and for mild slope we are getting depth more than the critical depth. So, these are some of the understanding regarding that critical depth, steep slope and mild slope. Well, and we will be using these mild slope and steep slope, all these in the classification of gradually varied flow, and that we will be discussing in the next class. Okay. Now, till now we have got some of the relationship that indicate the condition of critical depth. One is that specific energy is minimum for a given discharge, and the depth which make this critical condition, that is where we get the specific energy minimum, is called the critical depth, and that is why very basic definition we are getting this one. Then again we got that for a given specific energy, when discharge is maximum, that particular depth we refer as critical depth. But apart from this relation, we can derive some other conditions that indicate, that can be used as index for say critical depth. For example, let me start with this one, that is again say we got q square T by G A cube is equal to 1. This is our first condition that we are getting, and then from this condition what we can write, this we can rewrite in a different way, because we know that A by T is written as hydraulic depth D, So, using that D, how we can write this? This is equal to q square, then A we can write in two part, say G is there, then A we can write as A square 1, then another A, and T is there, this is equal to 1. Now, we know again that q is nothing but area into velocity. So, q by a is nothing but the velocity. Okay. So, this implies from this condition what we can write, that if I put this within bracket, then it will be nothing but v square and g will be there, and t by a that we can write as a by t here, this is equal to 1, and this is nothing but say v square by z d equal to 1. We can write that v square by z d equal to 1. Now, if we take square root of that expression, then what we are getting, that is v by root over g d, v by root over g d is equal to 1. Then perhaps all we remember what this expression stands for. V by root over g d is nothing but the Froude number. So, we can write that Froude number is equal to 1. Froude number is equal to 1. So, that is one of the very, very important relation that we get, and then we use this relation as an index sometimes. When say critical depth, then we see whether Froude number is equal to 1. If it is 1, then it is critical depth. If it is more than 1, then it is supercritical. If it is less than 1, then it is subcritical. So, this is used very much as an index. Well, then apart from this, we can have some other relation. Well, just let me take this part and let me see how we can rewrite this expression from here. From here, I could have gone in this direction also. Say v square by z d equal to 1, that I can write as say v square by, let me write a 2 here, and g let me write here, this is equal to d I am putting on that side, and as I am writing a 2 here, I am writing another 2 here. So, what this relation state? That is v square by twice g is nothing but the kinetic energy, that is kinetic head. And what is d by 2? It is half of the hydraulic depth. So, now if someone asks that what is the kinetic energy at the critical flow condition, then if we know the hydraulic depth, then we can say that yes, kinetic energy at critical flow condition is equal to half of the hydraulic depth. So, that is also another relation. So, combining all this relation, now we are in a position to summarize that what are the different relation that we have got, and this can be summarized as that conditions that we have for critical depth. So, what are the conditions for critical depth? First, of course, it is the specific energy is minimum for a given discharge, and always we should remember to mention this particular point, that is specific energy is minimum, fine, specific energy is minimum, but this is for a given discharge, and that depth is called as critical depth. Well, and second condition, as we could see, the discharge is maximum. Then here when we say discharge is maximum, here we need to speak about discharge is maximum for a given specific energy, this is also important. So, all these things, when the first condition we talk about, then we need to mention about specific for a given discharge. When you talk about the second condition, it is for a given specific energy. Then the third condition, just we have seen that critical depth is that depth at which velocity head is half of the hydraulic depth. Velocity head is half of the hydraulic head. And then another very important condition that we derive is called Froude's number is unity, that is Froude number is 1 for critical condition. Then another relation we have, we are yet to go into this one, but till now when but as we are summarizing this part, then we need to, I feel that we need to mention this point. Just like the specific energy, we got another term that is called as specific force, that is called as specific force, and that we did discuss when we were discussing the momentum concept and momentum equation. Rather, when we were starting from the momentum equation, then we were discussing that we got one term which was indicating that this term is containing force component, and that term we gave as a specific force. So, specific force, we got that specific force in two consecutive section. If we talk about say any two section, we were able to equate these things, of course, when all the forces are in balanced condition. Then, so that specific force if I draw, then for specific force also we can have a diagram. We can have a diagram, that is depth versus specific force. Just as we started with energy equation here, if we start with the momentum equation or the expression for momentum, if we start, then we can derive that relation, that is the specific force diagram we will derive, and that we will be doing in the next class. But still the relation what we will be getting is that specific force is minimum for a given discharge. Specific force is minimum for a given discharge. So, both specific energy and specific force is minimum at critical condition. Well, so these are some of the important point that we have derived. Then we need to go for computation of critical depth, because we are talking all this, that critical depth is that in this condition we get critical depth. Then for many computation we will be requiring to know what is the critical depth. That means we need to know what the critical depth is, and that is why suppose the discharge is given, a channel section is given, then we need to compute the critical depth for that particular channel, and that is what we refer as computation of critical depth. And always we will start from this relation that q square t by g a cube, q square t by g a cube is equal to 1, q square t by g a cube is equal to 1. Well, if we take a channel say if we take a trapezoidal channel just for example, then the side slope is suppose z, and if we say this is a critical condition of flow is occurring, that means this depth we are referring as critical depth y c. Well, now when it is y c, what will be this side? It is z y c, and that side is z y c, and then this bed width being b, the top width we can write as top width is equal to b plus twice z y c. Okay. And area, as we know that area of this section is equal to b plus z y c into y c, b plus z y c into y c. So, that way we can write that, because this plus that divided by 2 means basically we are getting b plus z y c and multiplied by the depth y c. So, we can write the area. Now, putting these expression here, what we can get, that this is equal to q square, then say t is equal to, we can write b plus twice z y c divided by say b plus z y c into y c. This is equal to 1, or we can this is this should be cube again, this should be cube, this is cube, q square t by g a cube, g will be here. So, this implies that q square by z we can keep in one side, and then we can write that b plus twice z y c is equal to, we can write the other part here, that is b plus z y c into y c whole cube is equal to 1. Sorry, these two are equal. Now, from here as we can see that we cannot separate out this y c if it is a trapezoidal channel, and it means again like our computation of uniform flow, for computation of critical flow also we cannot separate out y c for this sort of trapezoidal channel, and we need to go for trial and error procedure for computing critical depth. And of course, some approximate solution has been derived for this purpose also, and then for some simple cases like rectangular, triangular, we need to see whether we should go for trial and error, or we can go for a direct solution, or whether we have direct solution. So, all those we will be discussing in the next class in more detail. Thank you very much.